All right, so next up is Carlotta Mummolo from NYU.
Good afternoon. I'm going to talk about a stability method and its application into robot-assisted balance and locomotion. So the problem is this. If you have a multi-body system in any generic multi-contact configuration, the question is the system state balanced or falling? To answer this question, we provide definitions of what is a balanced and an unbalanced state. And these definitions are opposite and based on a specified contact. So from an unbalanced state, the system, in our definition, will inevitably have to change its contact. It's like the point of non-return. On the other hand, a system in a balanced state maintains the capability of reaching static equilibrium without requiring a contact change. The entire set of balanced state for a given system is, of course, contact dependent. It is identified by a balanced stability boundary in the center of mass state space. This boundary is constructed by sampling the COM position within its workspace, and for each position we evaluate the maximum allowable COM velocity perturbation such that the system maintains balance without changing contacts. In this work, we want to evaluate the balanced stability boundary of what we call a combined system. So there is a model of a lower limb exoskeleton, Mina V2, developed by IHMC, integrated with the model of a human body, both in the sagittal plane, and they result into this equivalent biped model that can make double and single contact with the environment, with the ground. And of course, the model is in a sagittal plane, as you can see in this study. These are the results of the balanced stability boundary of the combined system in double contact and single contact, respectively. Within this region, the blue region, the combined system maintains the capability of navigating through balanced states without ever requiring to change its contacts. As soon as the center of mass of the system exits this region, then an inevitable change in contact must happen sometimes in the future, and it could be, for example, the user is required to place his crutches on the ground, for example, during walking. But these are regions that are general, and they are true for the specific contact configuration and not just for a specific task, but any task in a double contact or single contact. Now, as a demonstrative example, we look at some walking trajectories that have been planned and recorded during walking with Mina V2. And the trajectories are for a one full step cycle, so they contain a transfer phase, which is a double contact, and a swing phase, which is instead a single contact. These experimental walking trajectories are mapped from joint space to center of mass state space, and we see them here in black in the results. So I show the forward walking projection is this way. So that trajectory, it contains a transfer phase and a swing phase for one full step cycle. So what we can observe in these results is that every state of this trajectory is a balanced state, because during the transfer phase, the trajectory is full within the double contact boundary, and during a swing phase, the trajectory is full within the single contact boundary, except for the very end. We see that at the end of the swing, the trajectory leaves the single contact stability boundary, but finds itself already within the next double contact stability boundaries, and that at the end is where the next step is going to happen. So what we are observing here is a trajectory that was performed experimentally with crutches that is being analyzed on top of stability boundaries that have been built for crutchless model. This is because we want to isolate the role of crutches in maintaining balance stability in the sagittal plane. So in conclusion, we provide a method to construct these contact-specific stability maps, and they are task-independent and control-independent properties of the legged system, in this case, the combined human exoskeleton system. For the Mina V2 walking, we saw that the step trajectories resulted as balanced at all times in the sagittal plane. So our guess is that maybe in the future a control law may exist such that the role of crutches, which are still used today, maybe in the future the role of crutches in sagittal plane stability stability might be reduced. And we'll keep doing similar analysis to evaluate controller performance and identify this role of crutches in stability in various anatomical planes, so not just sagittal, but also frontal. And that concludes my talk. And in conclusion, these stability boundaries can be considered in general as good references, so like maps that one can calculate a priori for a given system, and they can give good insights for the design, control, and evaluation of future robotic exoskeletons that allow for faster, more dynamic, but also stable walking. Thank you for your time, and do you have any questions?
So at the beginning, you talked about stability boundary in standing. Is that correct? The first one of the earlier plots, you showed the stability boundary just for what you can recover without stepping. Was that?
No, these stability boundaries, they are for a given contact configuration. It doesn't have to be standing. It can be like.
But in that contact configuration, it's the stability boundary from fall. But you're allowed to step to recover, or you're not allowed to step to recover.
If you exit, we don't predict a good recovery strategy. We just predict that there has to be some kind of recovery outside of it.
So the stability boundary is when it demands that you step.
Yeah, it's like similar the set of points of non-return.
The set of points of non-return.
Yes.
So if you're standing on one foot and the initial velocity is 0, how far outside of the support polygon is that stability boundary?
It's shown here. So maybe, yeah, here. So you are saying you're standing on one foot, so you want to look at the blue stability boundary.
Okay.
The blue one.
And we have an x velocity is 0.
Yeah, but you also have the single foot size is A plus B here.
Singles, and then the stability boundary seems like it goes to the edge of the foot plus 1 centimeter?
Yeah, actually in this slide it's better. Yeah, single contact. That's what you were
So how far outside this does it go? 1 centimeter or something like that?
Yeah, in terms of position, for this specific, of course depends on the model. For this specific model, you can go outside of the base of support 1 centimeter, 1.2.
Okay, so I just want to make a point.
Yeah.
In terms of people thinking that upper balance is important for upper body motions are important for balance, all the upper body motions contributed 1 centimeter to the balance.
In this model, yes.
Any additional questions? All right, well, thank you.